Okay, so here we are again. This is the third part of this chapter. And so we'll start up where we left off last night with the net change theorem, which basically is telling us that when a quantity changes, the new value equals the original value plus the integral of the rate of change over that interval. So we're going to see two different ways of expressing that idea. And I think you'll see that what you're basically seeing is that if we started, for example, here, wherever we are, so let's say we're at A, we go to B, that the change over this interval from A to B represents plus A, that is, gives us the new position B. But we can use this for some very helpful applications. And so, but you can see they both essentially represent the same thing. They're just algebraic rearrangements of each other. This is meant to indicate the change in the integral over the interval from A to B. In fact, you could actually write this step in here. This is the change between the 2 points in the integrals. So in other words, what you're trying to get you to see is if you start here and then jump up to here over the interval, you can calculate where your final position is by taking the starting point and then calculating the change over that interval. So let's do an example of this. You can see exactly what this is all about. So we start out with an engine that's turned on at time z, t equals 0 rather. Normally, whenever we have a time variable, 0 is meant to represent today. The rate of consumption of gas is 5 minus t cubed for the first hour. How much gas do we use just during the first hour? So I'm not sure what this function actually looks like. Why don't I see if we can get into Symbolab? 5 minus t cubed. Just out of curiosity more than anything else, you don't have to see a picture of it. But I think it helps to visualize what we're doing. So basically, what we're looking for is how much gas is being used during the interval from 0 to 1. From 0 to, let's say, 1 is right here. So how would we, oh, okay. So it looks something like that. So if we set this to find the intercept on the horizontal axis, we can just set it up like this, 0, because on the horizontal axis, y is 0. So yeah, this is the point. Cube root of 5 is 0. The cube root of 5 is approximately equal to, let's go to our calculator and find out. It's approximately equal to about 1.71. Okay, so what we're going to basically do is integrate this function over the time. This is t actually. Yes, it's the horizontal axis, but in this case, we're thinking of it as time from 0 to 1. Oh, I just realized I made a mistake here. This is 1. Sorry, I did it wrong. All right, let's try that again. This one was fine. This is the one where I messed it up. This is actually meant to be 1 comma cube root of 5. Sorry about that. Okay, now we're better. So in other words, the interval that we're looking at is from 0 to 1. X range, the T, I should say, ranges from 0 to 1 because this is the first hour, and this is the rate of consumption of the gasoline. All right, now we got it straight. So we're basically just integrating this the normal way. And so as we've seen before, we can break this up into 2 different pieces. As such. And then, of course, here we can move that 5 outside of the integral, and we end up with this expression. And then we can use the power rule. The integral of dt is just t. The integral of t cubed would be t to the 4th over 4. And so that's what we have. We evaluate between 0 and 1. Okay, let me just copy this into the next slide. Okay, so for this one, t, we evaluate between 0 and 1. And here we have t to the 4th over 4. I guess I could have left the 4 here. It's just, it's clear that when you have 0 over any constant, it's just 0. So we end up with 5 minus a fourth. So we end up altogether with 19 fourths. Okay, so that's telling us that during the first hour, that's how much gas we used. I assume it's measured in gallons. And what that represents is the area here under this curve. Okay, so there's what you're seeing here is that that's how much gas is being used. Now, integrating even and odd functions. Now, I just want to quickly remind everyone what this actually means, even and odd functions. So a function is even if f of x for every x equals f of negative x. So let me give you a perfect example of this. This is the function y equals x squared. So let's just say I pick 2 points at random, 2 and negative 2. In both cases, y is equal to 4. So in other words, f of 2 is 4, f of negative 2 is 4. And you can see that's clearly going to be the case no matter what x I choose. So therefore, this is an even function. Now, an odd function means that f of x equals negative f of negative x. So when would that happen? Let's say the function is y equals x cubed. And again, I'll pick 2 points at random. 2 corresponds with the y value of 8, but negative 2 corresponds with the value of y of negative 8. Because obviously when you cube a negative number, it's still negative. So that means that f of 2 is 8. F of negative 2 is negative 8, which equals negative f of 2. Or in other words, we could say f of x is negative f of negative x. And so therefore, this is an odd function. Okay, so I do have some graphs in here that show this. This is y equals x squared. This is y equals x cubed. So with an even function, we can break this up into 2 pieces. By the way, one of the characteristic features of an even function is symmetry from left to right. In other words, if you notice the left-hand side and the right-hand side match each other. With the odd function, what's basically happening here is that there's a symmetry, but it's with respect to the origin. So basically what you're seeing here is that the first and the third quadrants are mirror images of each other. And that could also happen with the second and the fourth quadrants. If you had y equals negative x cubed, that's exactly what you would get. It's still an odd function. It's just the symmetry is from the second to the fourth quadrant. Okay. And here, the symmetry is about the axis, the vertical axis. Okay. Anyway, so what we're going to do here is we're going to take advantage of this property of symmetry. Like, let's just use this as our example again. So let's say we're interested in the integral over the range from negative a to a. What they're basically saying here is that if you go from 0 to a and negative a to 0, they're both going to do the same. Okay, because of the symmetry. So if you notice here, what they're saying is what you can actually do then is rewrite this as from negative a to 0. And then 0 to a. But since these two equal each other, well, let's sneak this onto the next slide. That implies that the integral from negative a to a could be written as 2 times either one of these. So we'll just pick this one. Now that might save us some time. Who knows? It depends on the case, but it's good to know that this is true as long as it's an even function. You never know when it might save us some complications in our calculations. And then now what's interesting about the odd functions, since the symmetry is with respect to the origin, these are going to exactly offset each other. Okay, in other words, whatever area we have on the right is the negative area on the left, they're going to add up to 0. But one of them is they're negatives of each other. F of x dx between negative a and 0, which is the negative of this one, and that's why this is happening. Okay. All right. So let's look at some specific examples. We'll start with an even case. All right. Now, by the way, how can you tell? I mean, this is a tip-off. I mean, the exponent is an even number. It's almost certainly, I mean, you could prove it if you want to, but this one looks like it's going to be an even number, or even function rather. By the way, I forgot to mention that not every function is either even or odd. In fact, most of them are not neither. Some of them are even, some of them are odd, but a large number of functions are neither even nor odd. No function has to be even or odd. Let's put it that way. Now, if you take this graph, now this is what it looks like. Now, it is kind of weird. And this did come from Symbolab, by the way. This is what it actually looks like. And it does have that characteristic symmetry about the vertical axis. And so what that means then is that we can try this technique. First, let's do it. Well, let's do it the usual way first. Let's pretend we don't know about this. What do we have? 3x to the 8th. Minus 2 over the interval from -2 to +2. So, of course, we can break this up into two pieces. Let's move that down here, make it a little neater. So what I'm going to do is move the constants on the outside, of course. And then I'll use the power rule. All right, let's see. Now, actually, I'm going to move this 9 outside here. 3/9 is 1/3. And let's just solve it. All right, let me just quickly rewrite what we had. Well, actually, I have a better idea. Let's do this. Just to make it crystal clear, we don't want to skip steps. This is 3/9. I'll just write it as 3/9. But then here I'll convert it to 1/3. All right, so what does that leave us with? We have 2 to the 9th minus 2 to the 9th minus 2, 2 minus 2. 2 to the 9th is 5/12. And so it's negative. No, -2 is to the 9th power is negative 5/12 because it's an odd exponent. Okay, so we have to be careful with that. All right, so we got 1/3 of 1024 minus 8. Now, here's an interesting result. You might wonder if 1024 is divisible by 3. You probably remember this rule from somewhere along the way. Whenever you have a number like that, and if you're not sure if it's divisible by 3, what you do is you add up the digits. And if this number is divisible by 3, then so is the original number. Now, here, clearly, that's not the case. So we'll have 1024. By the way, there are actually similar rules for all of the digits 0 through 9. It's just that some of them are very, very complicated. And it may not be worth your while to memorize them, but they do exist. Okay, so you got 1024 over 3 minus 8, whatever that is. All right, let's do this. So what happens if we try our new technique? Okay, let's do it this way. We're going to break it up. -2 to 0. and then 0 to 2. And of course, since these are equal to each other, we can just rewrite it as 2 times this one. All right, so you can see now there's some benefit here because we only have to do this integration once and then multiply the result by 2. Okay, so again, using the power rule, get x to the 9th over 9th. The 3 has been moved to the outside. Here we have the integral of dx is just x. Negative 2 has been moved outside. And now we only have to do 2 evaluations, and at the end, we multiply by 2. So it could save us a little bit of work. So then, actually, I'm going to copy this to the next slide, just so you can keep track of it. Okay, so 2 to the 9th is 512. 0 is clearly just 0. Over here, we have 2 and 0. So when we do the algebra, I see there's a... No, this is not a typo. This is right. This reduces to 4. And this gives me 1536 over 9. Then we find a common denominator of 9. We ultimately end up with 1000 over 9, which of course is 3000 over 9, which is 1000 over 3. All right, so either way, we'll get the same result. All right, now, what about the old odd function? Now this, okay, it's a trig function, which means that there's a repeating, the curve just continues to repeat. It goes through a repeat series of repeating cycles. And now you can see it's an odd function because the symmetry is between this second and the fourth quadrants. Okay. And you can clearly see, I mean, the way it's been defined, these two areas clearly equal each other. So this one is negative, and this one is positive. And so they're going to exactly offset each other due to the symmetry. Okay, so let's prove it. Let's just go through this. So the integral is between negative and positive pi. So we're dealing with radians now. Minus 5 sine x dx. So yesterday we looked at this chart in the book. And you might recall that the integral of sine x dx is negative cosine x plus c. So remember, there's a chart in the back of the book if you're not sure, or you could actually go to Symbolab. But yeah, let's go back and revisit it. It was way at the end. Because you're, let's face it, you're not going to have all of these memorized. Way at the back. Oh, okay, I'll find it. Yeah, that's what I get for going to. Yeah. Here we go. Okay. You can see it's a huge set of tables, but the one we're actually after, there it is. Integral sine u du, negative cosine u plus c. So of course you can see where this is going. I mean, obviously, first we're going to move out this -5 outside of the integral. We're going to have -5 outside, and then we're going to evaluate negative cosine x between positive and negative pi. And again, if you have your calculator set on radians mode, you can just go and look it up. The cosine of pi is 1, or else you can lean on Symbolab. And oh, it's sorry, it's -1. Yeah, -1. That's right. So right, but this first term is negative anyway. So it's negative -1 minus 1, and then we end up ultimately with 0. Now, this next technique, the method of substitution, I think you'll find that you're going to get an awful lot of use out of this one. It just seems to show up often. I mean, constantly. It's everywhere. It's amazing how often this proves to be the best technique for any problem you might run into. So it's kind of, think of it as like a strategy. And so anyway, it's based on this, what you're seeing here is the logic behind what we're trying to do. But what you're basically doing is taking part of your integral and replacing it with the variable u. And then with that in place, you can then convert the dx part into du. And if you're lucky, you'll have a simpler integral to work with that you can easily find in those tables. In fact, that's one of the reasons why you look at the table, they all show as u's rather than x's, because this is the more general way of expressing these results. Okay, so anyway, let me just quickly show you an example of this. Now, at first glance, this looks like a nightmare. You could, in principle, expand this term by multiplying it by itself 4 times and then multiplying that final result by 6x, and you would have a pretty messy polynomial. But then you could apply the power rule to each term and you'd be done. But you know what? Maybe we don't want to go through all of that work. So what other alternative is there? Okay, so this is the genius of this method. We're going to start by defining u. And the strategy is to pick the messiest part of this expression for u. Let's do this. Now, how does that help us? Well, if this is u, this implies that du dx, which, by the way, a quick reminder, there's different ways of expressing a derivative. You might recall that y prime, f prime of x, and dy dx all represent the first derivative. Okay, dy dx is the instantaneous change of y with respect to x. Okay, so du dx here would be 6x, just 6x, using the power rule, because remember the derivative of that constant 4 is just 0. This in turn implies that du is 6x dx. Now, if we come back here and make substitutions, before we do that, we have to make one subtle change just to make it simpler. I'm going to combine these two terms. You'll see why in a second. And so what you've actually got here, remember, this is u, so you have u to the 4th power And all of this, we defined it as du. I think you'll agree that this is far simpler to integrate than this. All we have to do is use the power rule. And so let's see how that works out. Now we're not done because we still need to know what the actual function is in terms of x. But remember, we defined u to be 3x squared plus 4. Therefore, our result can be easily rewritten as 3x squared plus 4 to the 5th power over 5 plus c. Wow, that was a very clever way of getting around a very, very messy situation. The issue here is making sure you choose the correct u. If you pick the wrong one, you're going to wind up with an even messier expression. And that's how you know something's wrong. So you can feel free to try different ones, but as a rule of thumb, make sure u is, think of it as either the messiest expression or at the very least the one with the highest exponents, because whatever you choose for u, you still need a du in your expression. Otherwise, this is not going to work. Now, if you notice, I did not include the exponent of 4, because then I would not have had a du. I'm just choosing what's inside the parentheses so that I ultimately end up with u to the 4th du. That is easy to integrate. Then I substitute back the definition of u, and I'm all set. Okay. So now, of course, if you want, you can prove it. You can say, listen, is that for real? What is the derivative of this thing? And by the way, you don't have to worry about the constant for this because the constant just has a derivative of 0, of course. So what we'll do is now this requires us to take a bit of a detour and quickly review something that you learned in Calc 1. Just this part by itself, 3x squared plus 4 to the 5th power. Let's just say this is all I'm interested in. We need to use something called the chain rule. Five, 3x squared plus 4 to the 4th power times 6x. Now, how did I get all that? Because I'm treating this as a single term. The derivative, as you know, of x to the n is nx to the n minus 1. And that's what's happened here, okay? But because this expression is a function of x, it's not just x by itself. This is not complete. You need now the derivative of what's inside these parentheses, and that's where the 6x comes from. So that means just this part of the expression is 30x times 3x squared plus 4 to the 4th. So when I bring that back here, I've just got that 1/5 on the outside. I end up with 6x, 3x squared plus 4 to the 4th. And that, as you recognize, is our original function. So what this means is that we've done this correctly. So we'll get some practice, don't worry, with the chain rule and all the other rules we learned in Calc 1. But the chain rule is one that's easy to make mistakes with. The tricky part is remembering that when you're taking the derivative of the messy expression raised to some exponent, you still need the derivative of what's inside the parentheses. Okay. So anyway, so this U substitution method is going to save us a lot of grief if we use it correctly. All right. But again, it's just a question. It's not always easy to find which part of this thing should be the U. So it takes a little practice. But like I said, the rule of thumb is basically just make sure that whatever U you choose should be the messiest part of the integral. And that should take care of it. All right, so let's take a look at this one. Appears to me that this is the messiest part. And also the fact that this is raised to an exponent is sort of a hint. So why don't we choose U to be x cubed minus 3. Du dx would be 3x squared. Du would be 3x squared dx. So the first thing you want to ask yourself is, do we have u and du in this expression? If not, we've made a mistake. Even though we may have to rearrange this to prove it, you can see now that this is u squared, and this is what we mean by dx. Sorry, du. Uh-oh, what just happened? I think my tablet just froze up. Hold on one second. It happens. It's not a great tablet by any stretch of the imagination. Okay, so that means yes, and the answer is yes, we do have what we need. So what we're actually doing is equivalent to saying, what's the integral of u squared du? So we have u cubed over 3 plus c. Now all we have to do is make the correct substitutions back to x. Okay, so remember we defined u as x cubed minus 3. And so therefore, and that should do it. Oh, sorry, I missed the cube. So there it is. Okay, great. And once again, we can prove it. So by the chain rule, we have x cubed minus 3. Now there's already a 1/3 here, by the way. So we're going to have three x squared. Okay, so in other words, here we're going to have I wrote it incorrectly. And then the derivative of what's inside the parentheses is 3x squared. Now we'll simplify it. And that was the original function. Wow. All right. Now here's an interesting case. What should we choose for our u? Well, now again, now by the way, if you get the wrong u, you can just, and you'll find it out pretty quickly. You can go back and just try something different. That's not unusual. That the first time maybe you get the wrong u. I think it looks to me like we should go with x minus one for because it's inside the square root. So let's see if this leads to something useful. Now here's an interesting result. This x, if u is x minus one, that implies that x equals u plus one. So we actually have u plus one here. Well, guess what? That proved to be a bad choice because if you can see, it's a mess. Okay. Wow, that didn't turn out so well. Actually, no, you know what? Maybe we can salvage this. It looks like we're sort of done. We picked the wrong thing, but I'll tell you what, not necessarily. Here's why. Let's try this. I mean, just looking at it, it looks like, oh no, this can't be right. Let's think about it this way. Oh, let me move this. So I'll tell you, I would rather let me do it like this. I'm gonna write it as u to the 1/2 power. I think it'll just be quicker. So you can see what that means then is that we actually have u to the 1/2 du, u to the minus 1/2 du. And remember, based on that power rule, so what do we have here? U to the 3/2 over 3/2 plus u to the 1/2 over 1/2. And then, we can combine the constants at the end. We can do a little algebra. And now remember, when you divide by a ratio, a fraction, let's say like 3/2, it's equivalent to multiplying it by the inverse. So in other words, dividing by 3/2 is the same as multiplying by 2/3. And remember, u itself is equal to, we define it as x minus 1. That's it. We're done. So it looked like we're heading off the cliff, but no, we actually ended up with the right answer. Interesting. Wow. Okay. So Now, of course, we have to keep our eyes open too, because sometimes when you see, especially square roots when they get involved, it may be that this actually is some form. If you look again at our table, some of these are standard forms. In other words, if you had something like this or like this, you can see these actually just simplify to, let's say, arc cosines, arc tans, whatever the case may be. You should always keep your eye open for possibly cases that have a very specific meaning. Like if we had du over square root of a squared minus u squared, a is just some constant. That means we already are done because we have the arc sine of u over a plus c. We didn't have that, but I mean, in some cases you might actually have one of those cases, and then you obviously you'd be finished very quickly. Now, sometimes you can use the method of substitution, but only after performing a little bit of algebra. In particular, what may happen is you may not have exactly what you need for du. If the only part that's missing is a constant, then you might be able to take care of that yourself. All right, that's usually when we end up doing this technique. Let's say that du is 3x and all we have is x. Well, then what we can do is multiply by 3 and divide by 3. So we do have our proper du. All right, so let's take a look at this. Now, based on what we've been doing, it looks like we should probably let u be this piece. Du dx, 2x. Okay, so we have, see now, let's rewrite this. Do we have d, well, here's u, radical u, I should say. Is this equal to du? What's missing is the 2. So here's what we're going to do. That's not a problem. Here's why. Just copy this again. So just a quick reminder, we chose u to be x squared minus 5, which implies that du is 2x dx. So we're missing a 2, so watch what we can do. Oh, sorry, no, it's 2x dx. Now, did I change anything? I multiply by 2. And then I multiply by half, but it's the same thing as dividing by 2. So in other words, my result is exactly the same. I haven't changed anything. And yet what I've done is created a more convenient expression, because look what I have now. And of course I can rewrite this as u to the 1/2. And so I end up with 1/3 u to the 3/2 plus c. Oh my God. How clever is this? and we're done. Now, this will happen pretty frequently. I mean, the chances of you having exactly what you need um, are not great. It's not, I mean, well, I shouldn't say that, but I mean, it's not going to be that unusual that you're trying this technique and you realize that your DU is just missing a constant. If your DU is missing a variable, that's a different matter altogether. You can't just substitute one in there. Don't try to, like, for example, multiply by X and divide by X. That doesn't work. But if it's just a constant, then that's what you need to do, this technique. We're calling it substitution with alteration, meaning that you're tweaking it a little bit to make sure that your DU works correctly. All right, now what about this one? All right, well, I think we know where we're going. Since this expression has the highest exponent, it's the messiest. Let's try u equals x cubed plus 5 du is a dx is 3x squared. Therefore, du is 3x squared dx. Now you can see the problem. Even if I rearrange this thing algebraically, I don't have 3x squared, so I have to provide it myself, so to speak. And now I have what I need. I have u to the 9th, and I have du. Good. So I'll have 1/3. All right, I'll move that to the next slide. And then, of course, don't forget that u was originally defined as x cubed plus 5. And you're done. All right, so I think you'll find that that's a very, very useful technique. It'll be a very, I mean, when you're confronted with an integral like this, maybe the first thing you should consider is the substitution method. Now, that doesn't prove that it's going to be the right one, but in many cases it is, especially if you're dealing with integrals of polynomials. It's really incredibly helpful. We just have to be careful with it. Now, what do we have next? So let's go back to the notes. We're ready for section 1D, by the way. That was the end of C. So in part D, ooh, now this is where fun begins. Integrals, actually, surprisingly enough, integration with integrals and natural logs are actually quite straightforward. In fact, you can see a couple of examples here right in front of you. The integral of e to the x dx is just e to the x plus c. Now, a to the x is a little bit messier. A is some constant. It's like 3 or 7 or whatever. But what I'd like to point out to you, though, is that this first one is just a special case of the second one, because if you have this, using the rule down here, you would have e to the x over log e. Guess what? Natural log of e is just 1. So in other words, think of this as a special case of this second one. Yes, that's because it's base e. So in other words, the log of any base of b is just 1. So that if we have e to the x or some function of it, calculating integrals is actually going to be very straightforward. Now, what about this case? We don't have e to the x, do we? Oh no. So surprisingly enough, we can still use the method of substitution, but we're going to use it in a slightly different way. In other words, what's the messiest part of this expression? That would be the exponent. So let's try that. If u is minus x, du dx is minus 1, and du is minus dx. Now, we don't have that, do we? We have dx. So in other words, this is e to the u. This is not du. So what we can do is rewrite this as negative integral e to the minus x minus dx. Now we have e to the u, and we have du. Oh, whoops, I missed a mistake. And that's it. So, it's like I said, it's often the case you may not realize that it is an opportunity to use the method of substitution, but it's a very, very powerful technique that we can use quite often for many different situations where it may not be immediately obvious. As long as you can create a u and a du, you're good. Okay. And if you get the wrong one, you can try again. But sometimes the way you'll know that you've done it incorrectly or it's not working is that when you're done, you have a situation that's even messier than what you started with. Because remember, this whole technique, the whole point of it is to simply simplify what you're doing. If that's not happening, then something's wrong. Okay. So anyway, so I guess it's about that time. Maybe we can stop right here. Save some of the fun for tomorrow. And so what you might want to do is look in the back of this chapter and look for all of the examples involving the method of substitution in particular. But we will definitely have the opportunity to get more practice with this stuff. And because we need it. I mean, we've got to practice. The great thing about calculus is that it's something that you can learn with a lot of practice, even though it's very theoretical. So we'll get a chance to do that. And then we'll take it from there tomorrow. Okay. So have a good night.